Have you ever wondered what would really happen if an asteroid big enough to matter started drifting toward Earth, quietly and without any dramatic movie soundtrack behind it? Out in space, ancient rocks move through the dark in complete silence, and every so often, one comes close enough to make us ask real questions about danger, science, and how prepared we are. Tonight, here on Fall Asleep to Astronomy, we'll explore that idea gently. We'll look at how we spot these wandering objects, what they could actually do, and how humans are learning to watch the sky with steady, peaceful attention. No fear and no rush, just curiosity as you settle into the night. For now, settle in. When you're ready, we'll begin. Imagine, for a moment, a wanderer in space. Not a spaceship, not a comet with a glowing tail, but a single immense rock, about 6 miles wide, drifting through the dark like a slow, silent bullet. Now imagine that this rock is not passing peacefully by, but falling, drawn toward our world at a speed of around 12 miles every second. Its path locked in by gravity long before anyone could ever have a name for it. This is not a scene from a movie. About 66 million years ago, something very much like that actually happened. A giant asteroid came in from space and struck the place we now call the Yucatan Peninsula in Mexico. Where warm seas and coral reefs once shimmered, the rock hit with such force that it carved a vast scar into the crust, the crater we now know as Chicxulub. In that instant, the story of life on Earth bent sharply in a new direction. The moments that followed were beyond anything our minds can fully hold. The energy released was comparable to billions of nuclear bombs going off at once. Rock and water and air were torn apart and hurled skyward. Shock waves raced outward, shaking continents. Forests near the impact were ignited almost immediately, vast stretches of trees turning to fire. Across oceans, towering waves rose up and crashed into distant shores, tsunamis racing out from the wound in the planet's surface. But as terrifying as the first minutes and hours were, it was the sky itself that slowly became the greatest threat. When the asteroid hit, it did not just fling boulders and molten rock upward. It lofted enormous amounts of dust, soot, and sulfur into the atmosphere. Imagine the Earth's thin blue shell of air filling with fine, floating particles, as if someone had taken the dust of a shattered mountain and breathed it into the sky. These particles spread across the globe and formed a dense, hazy shroud, what scientists call an impact winter. Sunlight, which had bathed the surface for billions of years, was suddenly dimmed. The days turned colder and darker, not just for a few weeks, but for years. For a long time, the main suspects for this long-lasting darkness were soot from wildfires and sulfur from vaporized rock, both very effective at blocking the sun's rays. But more recently, researchers have turned their attention to something quieter and more easily overlooked: the finest dust of all. In a study published in the journal Nature Geoscience in October of the year 2023, scientists examined rocks that are about 66 million years old, collected from what is now North Dakota. That is an impressive distance from the original impact site near the Yucatan. And yet these rocks still held surprising amounts of fine dust. The particles they found were tiny, mostly between about 0.8 and 8 micrometers in diameter, so small that dozens of them could line up across the width of a single human hair. These minuscule grains proved to be crucial. Because they were so light, they could stay suspended in the atmosphere for an incredibly long time. The researchers concluded that this fine dust did not simply fall out after a few months. Instead, It likely lingered for as long as 20 years, with the first 5 to 8 years being the darkest and most severe. Imagine nearly a decade where the sun is constantly veiled, never fully bright, as if the world is caught in a permanent late twilight. With less sunlight reaching the ground, the planet's temperature dropped sharply. In the first year alone, global temperatures may have fallen by more than 18 degrees Fahrenheit on average. That kind of sudden chill would make the world feel alien, even to creatures who had lived through countless seasonal changes before. But perhaps the most important change was invisible: photosynthesis, the quiet process by which plants use sunlight to make food, began to fail. Without enough light, plants could not grow, could not repair themselves, could not continue. Slowly at first, then more quickly, they started to die. Once plants began to disappear, the rest of the food chain trembled. Herbivorous dinosaurs, those vast leaf eaters that roamed forests and plains, suddenly had less and less to eat. They weakened, starved, and dwindled. The predators that depended on them, the great carnivorous dinosaurs, found their prey growing scarce. Hunger moved up the chain like a shadow. In time, about 3/4 of all species on Earth vanished. It was not a single, instant blow, but a cascade of failures triggered by that first terrible impact and the long, dim winter that followed. The new study on dust did not change that overall picture, but it added a subtle and important detail. Dust, long treated almost as background noise compared to soot and sulfur, may have been one of the main reasons the darkness lasted so long. Soot and sulfur are very good at blocking light, but they tend to fall out more quickly. Dust, present in immense quantities and able to linger, might have quietly extended the crisis, stretching the chill and dimness across many years. The study also offered clues about survival. Not every living thing perished. Some plants and animals had strategies that allowed them to endure long periods of cold and darkness. Seeds could lie dormant in the soil, waiting for better times. Certain animals could burrow, hide, or slip into states similar to hibernation, slowing their bodies down until the skies cleared. These adaptations were like tiny lanterns of resilience, flickering in a long night. Yet, even with these insights, there are still mysteries. Freshwater ecosystems, lakes, rivers, and ponds pose particular puzzles. The new research casts doubt on some of the previously suggested survival mechanisms for organisms living there. It hints that we do not yet fully understand all the specific ways life failed or endured in the wake of a Chicxulub-scale strike. There are still quiet questions resting at the bottom of ancient lakes and seas. From that ancient catastrophe, our thoughts slide gently back into the present. The asteroid that struck 66 million years ago was not the only one of its kind. Space around Earth is not empty. It is filled with other wanderers, asteroids, comets, and smaller fragments that drift along their own paths around the sunday. Some keep a respectful distance, but others pass close to our orbit. These are what we call near-Earth objects, or NEOs. Near-Earth objects come in many sizes. Some are no larger than a house, or a car, or a grain of sand, destined to burn up quietly in the atmosphere if they ever meet our planet. Others are more serious. Mountains of rock or ice that, if they were to strike, could cause destruction on a regional or even global scale. Asteroids are mostly rocky remnants from the early days of the solar system, many of them lingering in the asteroid belt between Mars and Jupiter. Comets, by contrast, come from the colder, outer regions of the solar system. They are made of ice, dust, and rock, and when they sweep in toward the sun, they grow glowing comas and long, streaming tails like cosmic fireflies with luminous breath. The danger any one object poses depends on two simple things: how big it is and where it is going. A small asteroid on a harmless path is nothing to worry about. A large one on a crossing orbit is a very different story. To live with this risk, we need to know what is out there and how it moves. That is why space agencies such as NASA and the European Space Agency have spent years quietly building up a watchful network. Telescopes on Earth scan the sky night after night, looking for faint moving points of light. Each point might be an asteroid or a comet. The positions are recorded, then recorded again and again until a path can be traced. These objects are cataloged, their orbits calculated, and their future positions estimated, sometimes decades or centuries ahead. One important tool in this effort is a spacecraft called the Wide Field Infrared Survey Explorer. Originally built to survey the sky in infrared light, it was later repurposed for a mission focused on near-Earth objects, often referred to as NEOWISE. From its vantage point in space, it can see the heat emitted by asteroids, helping scientists determine their sizes and characteristics more precisely than optical telescopes alone. As our surveys grow more thorough, the amount of data becomes overwhelming for human eyes to track alone. This is where artificial intelligence steps in, like a patient, tireless assistant combing through old star images. In May of the year 2024, an artificial intelligence algorithm with a long name, Trackless Heliocentric Orbit Recovery, or Thor, like the thunder god for short, was able to pick out more than 27,000 previously unnoticed asteroids from archival telescope data. Imagine a single image of the sky containing up to 1.7 billion tiny points of light, stars, galaxies, noise, and maybe, somewhere in all that, a few faint asteroids. Thor can sift through all of those points, night after night, image after image, linking tiny changes and motions into coherent paths. Where a human might see only a blur of dots, the algorithm can recognize the slow drift of a rock moving against the fixed background stars and connect those dots into an orbit. Soon, a powerful new observatory will deepen this search even further. The Vera Rubin Observatory, planned to begin operations in the near future, is designed to scan the entire visible sky again and again with astonishing depth and speed. Armed with advanced artificial intelligence tools such as HelioLens C3D, this observatory is expected to discover and catalog millions of asteroids within its first few months, potentially doubling the current tally of known objects. It will be like giving humanity a new, much sharper pair of eyes. Even with all this, it is important to remember that no known near-Earth object is large enough to destroy the planet itself. Earth is massive and tough, but asteroids that are about 1 mile or more in size can still cause global catastrophes, events that would reshape climate, ecosystems, and human civilization. Because of this, NASA has been specifically tasked with finding and tracking these larger NEOs. As of the year 2021, more than 90% of the biggest objects have been discovered, and none of them pose an immediate danger to Earth. That does not mean there is no risk, but it does mean that for the largest threats, we are no longer entirely in the dark. Smaller objects, though, still matter. Even if they cannot plunge the whole world into an impact winter, they can cause severe damage on a regional scale. A city, a country, or an entire coastline could be at risk from an unlucky encounter with a rock a few hundred or 1,000 feet wide. One such asteroid has captured a great deal of attention. Apophis, named after an Egyptian god associated with chaos and destruction. Discovered in the year 2004, Apophis is a near-Earth asteroid roughly 1,000 feet across. Early calculations of its orbit suggested that it might have a small chance of colliding with Earth in the year 2029. For a while, this possibility cast a long, uneasy shadow over the future. But as more observations were made and the orbit refined, that shadow faded. With better data, scientists were able to rule out a collision. Apophis, it turned out, would pass by us, not into us. On April 13th of the year 2029, it is expected to sweep very close to our planet, within about 30,000 miles. To give that distance some context, it is closer than the orbits of some high-altitude satellites that circle the Earth. For astronomers, this close passage is not a threat, but an opportunity. During the flyby, Apophis will become bright enough in the night sky to be seen with the naked eye in some parts of the world. A moving point of light gliding among the stars. Telescopes on Earth, and possibly in space, will watch it carefully, measuring its motion, its spin, its shape, and its surface in unprecedented detail. From the quiet hills of California, a set of giant dishes waits in the desert night. This is NASA's Goldstone Deep Space Communications Complex, and when Apophis sweeps past Earth, those dishes will turn toward it like listening ears. Goldstone will send out pulses of radar, soft knocks of radio light that cross the darkness, touch the asteroid, and return with stories hidden in their echoes. By studying how those echoes change, scientists can trace the outline of Apophis, notice gentle bumps and hollows on its surface, and measure how quickly it spins. What would normally look like a tiny, moving dot of light in a telescope can, through radar, become a three-dimensional shape with craters, ridges, and subtle textures, like running your fingers over the surface of a stone you cannot quite hold. At the same time, the NEOWISE mission will watch Apophis in infrared light, where warmth itself becomes visible. In that glow, even small differences in temperature can reveal how rough or smooth the surface is, how quickly the rock heats up in sunlight and cools in darkness, and what its outer layers might be made of. Together, radar from Goldstone and infrared from NEOWISE let us do more than simply track where Apophis is. They help us understand what it is like as a tiny world of its own. Out in space, another traveler is making its way toward this encounter. NASA's OSIRIS-APEX spacecraft, once called OSIRIS-REx when it was visiting the asteroid Bennu, has been given a new mission. After releasing its precious sample from Bennu back to Earth, it did not simply retire. Instead, its path has been reshaped so that it can meet Apophis up close. From that close vantage point, OSIRIS-APEX will see details no ground telescope can resolve. Its instruments will map the surface, from larger boulders down to finer gravel and dust, and measure how sunlight reflects from different patches of rock. It will look for changes that may happen as Apophis passes near Earth and feels our planet's gravity tug on it. Slopes might shift, loose stones might move, and thin layers of regolith might slide. These subtle changes help reveal whether the asteroid is a solid block, a fractured body, or a loose pile of rubble clinging together under its own weak gravity. By studying Apophis in this way, OSIRIS-APEX also helps us step back and see the bigger picture. Asteroids are leftovers from the early days of the solar system. Inside them, in their minerals and structure, are clues to how dust and ice slowly gathered into larger bodies, and how worlds like Earth were eventually born. Learning what is inside an asteroid is a way of listening to the solar system's earliest memories. Apophis has drawn the attention of scientists far beyond NASA. Observatories around the world are planning to watch its flyby, each adding a different kind of observation. As part of a European effort focused on near-Earth objects, researchers at Julius Maximilian University in Würzburg have suggested small, nimble spacecraft that could travel alongside Apophis. One idea imagines a tiny satellite falling into step with the asteroid for roughly 2 months, flying nearby like a quiet companion and taking high-resolution images and measurements as Apophis turns in the sunlight. Another concept links such a small satellite with a planned European mission, often referred to as Ramses, so that together they can carry out richer, more detailed science than either could alone. Although Apophis itself does not pose a danger during its close pass in the year 2029, that encounter is a rare gift. Watching it so closely will improve our understanding of how asteroids behave near planets and will sharpen the tools we might one day need for planetary defense. To protect Earth from potential impacts, scientists have been developing several kinds of planetary defense techniques, each suited to different situations. One of the most straightforward is called the kinetic impact method. In simple terms, it means sending a spacecraft to collide with an asteroid at high speed. The spacecraft becomes a deliberate, controlled projectile. When it hits, its momentum is transferred to the asteroid, changing the asteroid's motion very slightly. Over months or years, that small change can grow into a large difference in position, enough to make the asteroid miss Earth entirely. This idea has already been tested in space. In the year 2022, NASA carried out the Double Asteroid Redirection Test, known as DART. The target was a small moonlet named Dimorphos, which orbits a larger asteroid called Didymos. DART flew straight into Dimorphos and was destroyed in the impact, just as planned. Afterward, astronomers measured how the moonlet's orbit had changed. It was now circling its parent asteroid more quickly than before, proof that the collision had successfully nudged its path. For the first time, humanity had changed the motion of a celestial body on purpose. Another proposed method is more gentle and is often called a gravity tractor. Instead of hitting the asteroid, a spacecraft would move close to it and stay there, holding a steady position for a long time. Even a relatively small spacecraft has mass, and mass means gravity. Over many months or years, the spacecraft's tiny gravitational pull can gradually draw the asteroid onto a slightly different course. It is a slow dance, relying on patience rather than force. This method has not yet been tried in space, but it is a promising option, especially if a threatening asteroid is discovered many years before a possible impact. In the most extreme situations, scientists have also considered using nuclear explosions as a last resort. In this scenario, a nuclear device would be detonated at some distance from the asteroid, not to shatter it, but to vaporize a thin layer of its surface. As that vapor rushes away, it creates a recoil, pushing the asteroid gently in the opposite direction and altering its path. This method could be very powerful, but it is also controversial. Using nuclear devices in space raises serious legal, political, and ethical questions, and international treaties place strict limits on such actions. Because of this, nuclear options are usually discussed only for very rare, worst-case situations. To prepare for possible future threats, space agencies and international organizations regularly run simulations and drills. In these exercises, they imagine discovering a fictional asteroid on a collision course with Earth. Over a series of days, they receive new observations, refine the imaginary asteroid's orbit, and discuss what to do. They practice how to share information quickly, how to coordinate between countries, and how to choose between different deflection strategies. In the year 2021, for example, NASA took part in an international planetary defense exercise organized by the International Asteroid Warning Network and the United Nations Office for Outer Space Affairs. The asteroid in that scenario was entirely made up, but the communication channels, decisions, and lessons learned were very real. Exercises like this help ensure that if a genuine threat is ever found, the world will not be starting from zero. All of these efforts rest on a deeper understanding of the objects that wander through our cosmic neighborhood. Asteroids and comets are often described as two separate families. Asteroids are mostly rocky bodies, thought to be remnants of the early solar system, many of them orbiting in the belt between Mars and Jupiter. Comets tend to come from the colder outer regions of the solar system and are made of ice, dust, and rock. As they approach the sun, their ices vaporize, forming glowing comas and long, delicate tails. Yet, some objects blur the line between these two groups. One such body is called 2005 QN173. Discovered in the year 2005, it orbits the Sun in the main asteroid belt and takes about 5 years to complete one loop, which makes it look like a typical asteroid at first glance, but its behavior tells a more complex story. In the summer of the year 2021, the Asteroid Terrestrial Impact Last Alert System in Hawaii noticed that 2005 QN173 had grown a tail. Follow-up observations by the Las Cumbres Observatory and the Zwicky Transient Facility confirmed this comet-like activity. The tail stretched for roughly 450,000 miles, a long, slender plume of dust extending behind the small core. This tail suggests that the object's surface contains icy material. As it moves closer to the Sun, that ice does not melt into liquid, it sublimates, turning directly from solid into gas. The gas carries dust particles away, forming the tail. In that way, 2005 QN173 behaves like a comet. Even though it travels in an orbit more typical of an asteroid, there is a puzzle hidden in the shape of the tail. Its narrowness implies that the dust particles are leaving the surface at very low speeds, hardly faster than a slow drift. Normally, such small speeds would not allow dust to escape the body's gravity. One possibility is that the core of 2005 QN173 rotates quickly, so that the combination of rotation and gas flow helps lift dust into space. Whatever the explanation, this strange dual behavior shows that the boundary between asteroids and comets is not sharp. There is a spectrum of objects in between, each with its own quiet story. Beyond individual curiosities like this, there are many near-Earth objects that we watch more carefully because their paths cross, or nearly cross, Earth's orbit. The European Space Agency keeps a detailed risk list, which catalogs objects with a non-zero chance of colliding with our planet at some point in the future. The list currently includes more than 1,600 targets. For each one, scientists estimate its size, speed, and the probability that it might one day strike Earth. To make these risks easier to compare, they use a measure called the Palermo scale. This is a logarithmic scale that combines an object's size, impact energy, and impact probability into a single number. Most near-Earth objects sit at very low values on this scale, meaning their risk is much smaller than everyday hazards we already accept without thinking. A few objects rank higher and are watched more closely as new observations refine their orbits. Large asteroids, especially those about 1 kilometer in diameter or more, are a special concern because of their potential to cause global damage. Fortunately, NASA and other space agencies have already identified and tracked more than 90% of these big bodies, and none of them are currently on a path that threatens Earth. That knowledge removes some of the deepest worries, even though it does not erase all risk. Smaller objects, while unable to cause worldwide extinction events, can still be extremely dangerous on a regional scale. The meteor that exploded over Chelyabinsk in Russia in the year 2013 released enough energy to shatter windows and damage buildings over a wide area, injuring thousands of people. The Tunguska event in Siberia in the year 1908 flattened vast stretches of forest, likely caused by another object exploding in the atmosphere high above the ground. Both events happened in relatively remote or sparsely populated regions. If something similar occurred above a major city, the damage would be far more severe. These past events remind us that even smaller asteroids are worth tracking. They also highlight why it matters that we keep improving our surveys and our defenses. As we continue to discover and track near-Earth objects and refine our planetary defense strategies, international cooperation and technological advances remain critical. By understanding the diverse nature of these celestial bodies and preparing for potential threats, we can protect our planet and ensure a safer future for generations to come. Every few years, something quiet but powerful stirs beneath the broad blue surface of the Pacific. From far away, the ocean may look calm and unchanged, but deep inside it, a vast pulse of warmth is gathering, stretching across thousands of miles. It is a climate rhythm with a gentle name in Spanish, El Niño, the boy. Yet its touch can reshape weather all around the world. When El Niño awakens, the surface waters of the eastern and central Pacific become a few degrees warmer than they usually are. It may not sound like much, just a slight rise in temperature. But for the atmosphere above, that change is enormous. The ocean and the air are partners. When one shifts, the other responds. This pattern was first noticed centuries ago by fishers along the coasts of South America, who saw the warm waters arrive around Christmas and named the phenomenon for the Christ child. Over time, we have learned that El Niño is not a local quirk. It can bring torrential rains and catastrophic floods to parts of South America, and at the same time, stubborn droughts and wildfires to distant lands like Australia. It can change how much carbon dioxide is absorbed by the ocean and nudge global temperatures upward for a year or two. El Niño usually begins in the east-central Pacific, and so the countries that border that part of the ocean often feel its first, sharpest effects. Marine life that has adapted to cooler, nutrient-rich waters suddenly finds itself in a warmer, poorer sea. Developing nations whose economies lean heavily on fishing or small-scale farming may have very little cushion against rapid climate swings, and so they feel each shift like a direct blow. Yet El Niño is only one face of a larger pattern called the El Niño Southern Oscillation, often shortened to ENSO. This pattern has three main phases: the warm El Niño, its cool counterpart La Niña, and a neutral state where neither strongly dominates. Together, they form a kind of slow breathing of the Pacific climate. La Niña, the girl, is the mirror image of El Niño. Instead of warming, it brings a pronounced cooling of the surface waters in the eastern and central Pacific, sometimes by many degrees Fahrenheit below the long-term average. The atmosphere responds in its own way. In some regions, La Niña is linked to stronger rainstorms, more frequent floods, and sometimes more intense hurricane seasons, especially affecting areas like the southern United States and parts of Canada. Where El Niño might bring dryness and heat, La Niña may bring chill and deluge. Both El Niño and La Niña are difficult to predict far in advance. They tend to appear every 2 to 7 years, but not like clockwork, and their strength varies from modest to extreme. El Niño often lasts around 9 to 12 months. La Niña can linger longer, sometimes 1 to 3 years. For communities trying to plan for crops, water, and safety, this irregular heartbeat is a constant challenge. To understand why these phases matter so much, it helps to picture how the Pacific behaves under normal conditions. Across the tropical ocean, trade winds usually blow from east to west, from the coasts of the Americas toward Asia and Australia. These winds push warm surface water westward, piling it up near Indonesia and northern Australia. In response, colder, deeper water wells up along the western coast of South America, rising to replace the water that has been pushed away. This process, called upwelling, brings nutrient-rich water to the surface, feeding plankton, fish, and the communities who depend on them. Warm water heats the air above it, making that air rise, cool, and condense into clouds and rain. Over the warm western Pacific, towering storm systems form, releasing heat high into the atmosphere. Cooler, drier air aloft drifts back toward the eastern Pacific, sinks, and joins the trade winds again. It is a loop, a circulation that helps keep the pattern in place. Winds push warm water feeds storms, storms help drive the winds. When this delicate balance is disturbed, El Niño or La Niña can emerge. During El Niño, the trade winds weaken. With less push from east to west, warm water spreads back toward the central and eastern Pacific, and upwelling along South America's coast is reduced. The normally cool regions near Peru and Ecuador grow unusually warm. Rainfall patterns shift. Some tropical areas see much more flooding rain, while others, especially farther west, slip into drought. Small, specific places feel these shifts very directly. In the protected Pu'uwa'awa'a area in Hawaii, for example, a typical January might bring around 3 inches of rain. During the El Niño conditions of the year 2010, only a thin fraction of that amount fell. Land that expected gentle, regular showers instead endured a dry, hesitant sky. Over time, the ocean can swing back the other way. In La Niña, the trade winds strengthen, pushing even more warm water toward Asia and enhancing upwelling in the east. Cold water spreads more widely along the equator. The western part of the United States and the northern portions of South America may feel cooler, wetter conditions, while parts of the Indian Ocean basin may become warmer, changing rainfall there. The regions hugging the Pacific's shores often bear the brunt of both phases. In the 19th century, a series of strong El Niño and La Niña events contributed to severe droughts and floods in countries such as India, China, and Brazil. Historians and climate scientists estimate that, across those crises, tens of millions of people, perhaps on the order of 30 to 60 million, lost their lives to hunger, disease, and hardship. In the 20th century, roughly 24 El Niño episodes were recorded, many of them bruising crop harvests in Western countries and harming wildlife populations, including colonies of sea lions that depend on stable fisheries. Some of the most frequent victims lie along the western coast of South America, in countries like Peru and Ecuador. Their economies lean heavily on the ocean, on fish, and the fertilizer made from them. During El Niño, reduced upwelling starves the surface of nutrients, and fish populations can collapse. Warmer waters and changing currents disrupt entire food webs. At the same time, heavier rains fall on land. Fields may be washed out, fertilizers leached away, roads and homes damaged by floods and landslides. What the ocean withholds in one place, the sky gives too much of in another. Far to the west, places like Indonesia and Australia often face the opposite problem: drought. Reservoirs and rivers shrink, soils crack, and crops struggle to survive. Livestock suffer, and people face increased health risks as heat and dryness strain their bodies and their communities. Land that once felt lush can, in a strong El Niño year, feel brittle. Across Africa, the pattern is patchy but powerful. Eastern countries such as Kenya and Tanzania and parts of the Americas may endure more frequent heavy rains and flooding, while South-Central nations like Zambia and Mozambique confront the specter of drought. In the southern United States, including states like Texas, El Niño often brings increased rainfall. In California, those additional rains can sometimes be a blessing, refilling reservoirs and nourishing crops such as limes and avocados. In Canada, winters during El Niño years may feel softer, with milder temperatures than usual. Even Antarctica is not untouched. In some parts of western Antarctica, El Niño is associated with slightly warmer conditions and increased snowfall. Yet, as upwelling patterns change and ocean waters near some coasts warm, floating ice shelves can begin to thin and melt from below. La Niña, with its tendency to cool certain waters, can help ice shelves regain some mass, offering a partial counterbalance. The polar regions, so distant and seemingly separate from human life, still sway to the same Pacific rhythm. Europe, too, feels a distant echo, though it is harder to trace directly. El Niño tends to bring colder, drier winters to parts of the European continent, conditions that can stress soils and crops. In the 18th century, strong El Niño-related climate anomalies likely contributed to poor harvests across Europe, which some historians suspect played a role in the tensions that led up to the French Revolution of 1789. In the 19th century, similar patterns helped set the stage for several severe famines in Asian and European countries. All of this might sound like old history, but El Niño and La Niña are still very much alive today. The most recent pair of strong events before our current decade unfolded in the years 2015 and 2016. The year 2016 became, at that time, the hottest year ever recorded globally. That El Niño was one of the most intense in roughly half a century, and its consequences were felt almost everywhere. During that episode, equatorial Pacific waters remained warmer than usual through the entire year. In the central Pacific, sea surface temperatures rose dramatically above their long-term averages, reaching peaks that scientists described as some of the highest since systematic records began in the 1860s. On land, the warmth and shifting rainfall patterns deepened existing vulnerabilities. More than 60 million people around the globe experienced food insecurity, linked, at least in part, to the droughts and crop failures associated with that event. Every continent felt some effect, directly or indirectly. In Australia, the eastern and northern regions slipped into severe drought. Rivers fell, soils dried out, and vegetation became tinder. The fire season, which might normally start later, arrived early. Across the landscape, about 125 significant fires were recorded, burning through forests, grasslands, and scrub. One of the saddest chapters unfolded in Tasmania. There, in places that had rarely, if ever, experienced fire in living memory, Flames pushed into ancient rainforests and delicate wetlands. Ecosystems that had grown in the quiet assumption of dampness and cool shade were suddenly exposed to heat and smoke. Large areas of nature in Tasmania, including rainforest and swamps that had hardly ever experienced fires before, were severely damaged. During that same intense El Niño, the ocean did not only fuel droughts and fires on land, it also bruised life beneath the waves. In many places, the warm waters triggered some of the worst coral bleaching ever recorded. Corals, stressed by heat, expelled the tiny algae that live inside them and give them color and food. Without those partners, the reefs turned ghostly white and became fragile, far more likely to sicken and die. Whole underwater cities, built over centuries, were suddenly at risk in a matter of months. On the surface, the seasons themselves felt skewed. In Australia, the spring and autumn of the year 2016 were among the driest on record. Fields that depended on gentle, regular rains instead lay under hard, empty skies. Harvests suffered, and the heat strained the systems that supplied the country's most important export commodities, including mineral ores. When the largest exporter in a region struggles, the effects ripple outward through ships, markets, and the lives of workers far from the fields themselves. Across Asia, the picture was just as uneven and just as demanding. In the Philippines and Indonesia, the vast majority of the land, something like more than 4 out of every 5 areas, endured severe drought. Rivers shrank, reservoirs dropped, and farmers watched their crops wither. In Indonesia, parched forests and peatlands ignited, and large-scale fires burned for weeks. The smoke did not respect borders. It drifted into neighboring countries such as Singapore, Malaysia, and Thailand, filling the air with haze, irritating lungs, and dimming daily life. Those fires also disrupted the production and export of palm oil, an ingredient quietly present in countless foods and household products. As supplies tightened, prices climbed, and the cost of living rose for people far beyond the forests where the flames actually burned. At the same time, rice harvests in countries such as Vietnam and Thailand dropped, hampered by water shortages. India, facing its own stresses, reduced exports of rice, sugar, cotton, and corn. In northern China, drought took hold, while southern regions struggled with heavy rains and floods. It was as if a single invisible hand had reached through the climate, tilting fortunes up and down across a whole continent. South America, closer to the heart of the Pacific changes, felt the full force of weather-related disasters. In one El Niño year, Peru suffered severe flooding and landslides. Around 5,000 people lost their homes, and shrimp production fell as the coastal environment was disturbed. Farther south, in Paraguay, Brazil, and Argentina, rising waters forced about 150,000 people to evacuate flooded areas. In Argentina, a massive locust infestation swept across agricultural regions, chewing through crops already weakened by strange weather. In Colombia, after a period of harsh drought, the return of rain in April of the year 2016 came too late for many. Food shortages tipped into famine in some areas, and approximately 2.3 million people required humanitarian assistance, according to United Nations estimates. In the Caribbean, drinking water grew scarce enough that the island nation of St. Lucia declared a state of emergency. In Brazil, uneven rainfall and heat contributed to rising coffee and sugar prices, which then echoed through global markets, touching everyday items like a morning cup of coffee or a spoonful of sweetener on the other side of the world. The African continent, too, felt the strain. In South Africa, food production fell by several million tons, leaving a gap that had to be filled through imports or not filled at all. In parts of Zimbabwe, as much as 3/4 of the harvest was lost. In Ethiopia, around 10 million people needed humanitarian aid, and close to 500,000 children were treated for acute malnutrition. Across the globe, roughly 60 million people experienced hunger linked to that El Niño. Each number representing a family, a face, a story. Unfavorable weather also opened the door to disease. In parts of South America, flooding created ideal conditions for mosquitoes, and the Zika virus began to spread more widely, bringing with it fears of birth defects and other complications. In Africa, outbreaks of cholera and Rift Valley fever were recorded, along with increases in malaria in certain regions. Water that was once a source of life became, under these new conditions, a carrier of risk. Animals suffered alongside humans. Marine birds found their usual feeding grounds altered or empty, as warmer waters reduced the availability of fish. Small mammals lost food and shelter as fires and drought reshaped their habitats. Hungry predators, deprived of their normal prey, sometimes turned to farm livestock, leading to further losses for people already struggling. At the same time, some invasive species thrived. Locusts, like those that plagued Argentina, and certain types of tree frogs expanded their numbers, damaging crops and helping diseases spread more easily. All of this reminds us that El Niño and La Niña are not distant curiosities. They are powerful, shifting rhythms in the climate system, and their consequences reach deeply into food, water, health, and ecosystems. That is why meteorologists watch the Pacific so carefully, looking for early signs of change. In recent analyses, experts have already seen patterns suggesting that another El Niño is likely to form in the late summer of the year 2023 or in the very early part of the year 2024. According to researchers from the National Oceanic and Atmospheric Administration, such as Dylan Amaya, and leaders of the World Meteorological Organization, including Secretary General Petteri Talas, there is a real possibility that new global temperature records could be set as this event unfolds. One reason for this concern lies in what came just before. The world has recently passed through an unusually long La Niña period that lasted for about 3 years, ending around March of that time. During La Niña, some of the ocean's excess heat can be stored away beneath the surface. When the pattern flips back toward El Niño, that stored warmth can be released again, adding to the usual signal and strengthening its effects. It is as if the ocean has been quietly charging a battery of heat, now ready to discharge. No two El Niño events are exactly alike. Their timing, strength, and the background state of the climate all differ. So it is hard to say whether the world will see a repeat of the 2015 to 2016 impacts. Still, scientists can outline possibilities. A climate science researcher named Teresa Castro, for example, has described several likely consequences for global weather in the years 2023 and 2024. First, she notes that average ocean temperatures in key regions could rise by several degrees Fahrenheit above normal, and during the peak of El Niño, they might climb even higher, just as they did during the strong event of 2015 and 2016. It is too early to say exactly how intense this warming will be, but even modest changes at the ocean's surface can have large effects on weather patterns and ecosystems. Second, she points out that Australia, after the long La Niña, has recently experienced plentiful rainfall in many areas. The land may feel green and full, but the underlying trend is that the continent's average temperature has already risen by several degrees Fahrenheit compared to the beginning of the 20th century. If a new, very hot year arrives on top of that background warming, fire seasons could start earlier, and the risk of extreme heat waves would grow. Third, there is concern that South America could once again face humanitarian crises similar to, or even worse than, those of the previous strong El Niño. Droughts and floods could threaten crops, water supplies, and infrastructure. When water stands in warm air for long periods, mosquitoes often flourish, raising the likelihood of diseases such as malaria, dengue fever, and the Zika virus, returning or spreading more widely. Prolonged abnormal heat can also contribute to health problems like heat stress, complications in pregnancy, and increases in miscarriages, especially in places where medical systems are already stretched thin. Forests in the Amazon basin, as well as tropical forests in parts of Africa, India, and Australia, may be placed under great strain by prolonged droughts. Trees grow more slowly or die back, and the lush canopy that usually drinks carbon dioxide from the air could thin. When vegetation growth slows, less carbon dioxide is absorbed from the atmosphere, leaving more of this greenhouse gas aloft, and gently reinforcing the warming that helped create the problem in the first place. Fourth, Northern Europe may be more likely to face cold, dry winters, while Southern Europe could see an increase in heavy rainfall. The North Atlantic Ocean, influenced by shifting winds and heat distributions, might even experience a relative cool down in some areas. For people living through those seasons, the changes might feel like colder, crisper winters in some places and more frequent storms in others. During El Niño, access to food and clean drinking water tends to become more fragile. Crops fail in some regions, fisheries suffer in others, and the supply chains that move food around the globe are strained. Australia, Brazil, Peru, and many African nations that struggled during the 2015 to 2016 episode may, unfortunately, face the risk of renewed food and economic crises. Exports of key agricultural products, livestock, minerals, and fuel may decline sharply, sending subtle but real shocks through the global economy. In the United States, forecasts from the National Oceanic and Atmospheric Administration suggest that the eastern part of the country could see heavier than usual rainfall, while the southwestern and southern regions may endure strong heat waves. These patterns can affect everything from energy demand and wildfire risk to river levels and crop yields. Economists are also trying to understand the longer-term cost of these climate swings. A study from Dartmouth University, led by researcher Christopher Callahan, has estimated that the economic impacts of a strong El Niño could amount to around $3.4 trillion over the 5 years that follow, as losses accumulate across agriculture, infrastructure, health, and industry. These are not just numbers on a page. They represent delayed projects, lost jobs, strained budgets, and the quiet erosion of security for millions of people. Looking ahead, many climate scientists worry that El Niño and La Niña events may become more intense or more frequent as the planet continues to warm. Stronger swings in ocean temperature can do more damage to fragile systems, particularly tropical forests that depend on stable patterns of rain and heat to regenerate. If these climate rhythms become increasingly disrupted, whole forest ecosystems may struggle to form and recover in the ways they once did. One of the main reasons for this growing vulnerability is the steady rise of greenhouse gas emissions from human activities. As more carbon dioxide and other heat-trapping gases accumulate in the atmosphere, the baseline temperature of the planet increases. High global temperatures that once seemed exceptional begin to feel more like the new normal, and each additional El Niño event then starts from a warmer, more stressed world. All of this, the fires, the floods, the bleaching reefs, the shifting diseases, the economic shocks, is not meant to frighten so much as to clarify. The possible worsening of weather and climate conditions is not a distant, abstract idea. It is a gentle but insistent signal, reaching us through data, through the stories of farmers and fishers, through the quiet changes we notice in seasons we thought we knew. It asks something simple and difficult of us at the same time: to take better care of the air, the water, the forests, and the living web we share. Only when we care for the environment, gently and together, do we begin to soften these risks and shield ourselves from the most painful possibilities. And when we talk about caring for our world, sooner or later, we find ourselves looking toward the great engine that makes almost everything here possible: our Sunday. Out in the wide, dark ocean of the solar system, the sun hangs like a brilliant heart. It is a mystery and a comfort at the same time, a source of light, warmth, and energy that has shaped every cloud, every wave, every leaf you have ever seen. To understand our changing climate, our fragile atmosphere, and even the technology that surrounds us, we need to understand this star that never truly sets. For more than a decade now, one quiet guardian has been watching the sun for us without blinking. NASA's Solar Dynamics Observatory, often called SDO, was launched into space on February 11, 2010. Its mission is simple to say and endlessly deep to explore: to study the sun in exquisite detail and unravel some of the secrets of how it behaves and how it touches every corner of our solar system. Imagine a world where each passing second reveals some new pattern in fire and plasma, where loops of glowing gas arch higher than the diameter of Earth, and waves of energy roll across the solar surface like invisible tides. That is the world SDO inhabits. From its orbit high above Earth, it turns its instruments toward the sun and takes images again and again, capturing new views every few seconds. Each picture is a tiny piece of a vast puzzle, a single frame in a never-ending film about how our star lives and breathes. Once it was settled into its orbit, SDO began its long watch with an unobstructed view of the Sunday. Its main purpose is to help us understand how the sun influences Earth and the wider solar system by looking closely at the solar atmosphere, the thin, blazing layers of gas that surround the star's surface. To do that, the spacecraft carries a suite of instruments, each one like a different pair of glasses, tuned to a particular way of seeing. One of the most important of these is the Atmospheric Imaging Assembly, often shortened to AIA. You can think of AIA as a camera that can see colors our eyes cannot. It observes the sun in 10 different wavelengths of extreme ultraviolet and visible light, each one corresponding to a different temperature of solar material. Cooler regions, hotter regions, and everything in between glow differently at each wavelength. By combining those views, scientists can build a layered portrait of the sun's surface and atmosphere. Through AIA, sunspots no longer look like simple dark freckles. They become windows into twisted magnetic fields and cooler, turbulent patches. Above them, great coronal loops, arched bridges of plasma following magnetic lines rise and fall, bright and delicate. Over the years, AIA has quietly taken more than 425 million high-resolution images, a continuous stream of data that paints a vivid, living picture of the sun's restless face. Why do we watch the sun so carefully? Because almost everything in our cosmic neighborhood answers to it. The faint auroras that shimmer near Earth's poles, the subtle changes in the upper atmosphere that can drag on satellites, the space weather that can disturb radio signals or power grids, all of these trace back, in some way, to storms and rhythms on the Sunday. To understand our own environment, it helps to know what the star at its center is doing. Through the patient eye of AIA, we have watched solar flares ignite like sudden flashes, magnetic fields twist and snap, and giant eruptions of solar material billow into space. Processes that were once only guessed at in theory are now seen unfolding in real time. The Solar Dynamics Observatory has turned the sun from a distant, unchanging disk into a dynamic world whose moods and cycles we can follow. One of the strengths of SDO is its ability to see the sun at many wavelengths, each one opening a different window into the solar atmosphere. Among these, the extreme ultraviolet wavelength, around 17.1 nanometers, holds a special place. At this wavelength, SDO peers into the corona, the outermost layer of the sun's atmosphere, where temperatures soar to millions of degrees and some of the most dramatic solar activity occurs. Through SDO's instruments, the corona is no longer a dim halo glimpsed only during total eclipses. It becomes a bright, detailed landscape of light and motion. We see those coronal loops, giant arcs of plasma tracing the sun's magnetic field. We watch as parts of the corona erupt outward in coronal mass ejections, sending vast clouds of charged particles into space. These observations are not just beautiful, they are essential for understanding how solar storms are born and how they might one day wash over Earth, affecting satellites, astronauts, and even systems on the ground. SDO's relentless pace, taking images every few moments, across many wavelengths, lets us watch the sun's outer atmosphere evolve, almost as if we were standing beside it. Little flickers that might once have been missed now appear as part of larger patterns, building into flares or fading into quiet. Every wavelength reveals a slightly different story, from the churning photosphere below to the glowing, extended corona above. Beyond individual flares and eruptions, SDO has also helped us explore one of the sun's deepest rhythms, the roughly 11-year solar cycle. This cycle is marked by the ebb and flow of magnetic activity on the sun, seen most clearly in the number of sunspots that dot its surface. During solar maximum, the sun is busy and blotched, with many sunspots, frequent flares, and more coronal mass ejections. During solar minimum, it can look almost bare, with fewer active regions and a calmer, quieter face. Because SDO has been watching for more than a decade, it has nearly followed a full cycle from one phase back to the other. It has seen the sun at its most restless and at its most subdued, following how sunspots appear, grow, and decay, how magnetic fields rise, twist, and reconnect, and how the number and strength of flares change with time. These long, continuous observations are like listening to a slow, low drumbeat beneath all the sudden bursts and flashes. Along the way, SDO has captured some spectacular events in exquisite detail. Coronal mass ejections, huge eruptions of plasma and magnetic field that can carry billions of tons of solar material into space have been recorded from their first stirrings on the sun's surface through their growth and departure. Solar flares, intense bursts of radiation across the spectrum, have been tracked in multiple wavelengths at once, helping scientists understand which regions flare, how fast they rise, and how they fade. The observatory has also watched quieter, rarer events: the silhouetted passage of planets across the sun's disk, known as transits. When a world like Venus or Mercury glides between the Sun and Earth, it appears as a small, dark dot crawling slowly across the bright surface. SDO's sharp eye turns these alignments into precise experiments, allowing scientists to study the thin layers of the Sun's atmosphere and to refine techniques for observing distant exoplanets around other stars. To gather such a rich harvest of data for so long is never simple. Space exploration is full of challenges, and SDO has faced its own share. At times, Earth itself moves between the spacecraft and the Sun, casting SDO briefly into shadow. On some orbits, the Moon slips across the line of sight, creating sudden solar eclipses in the spacecraft's view. Each of these moments interrupts the steady watch, and each must be carefully accounted for in the data. There have also been technical difficulties that tested the mission's resilience and the creativity of the teams on the ground. Instruments age and need careful tending. In the year 2016, for example, the atmospheric imaging assembly experienced problems that required thoughtful troubleshooting and adjustment. These and other obstacles have made SDO's path anything but simple. From Earth's shadows and lunar eclipses to instrument challenges like the AIA issue in that year, the Solar Dynamics Observatory's journey has been, in many ways, as thorny and winding as the magnetic fields it so patiently observes on the Sunday. Even a tireless observer like the Solar Dynamics Observatory has to put up with a few interruptions. One of its most persistent challenges comes from two very familiar neighbors, Earth and the Moon. From time to time, as SDO orbits and the geometry lines up just so, our planet or its satellite slips directly between the spacecraft and the Sunday. These are not surprising events. They are part of the natural dance of orbits, but they do briefly close the window. Around the times of the equinoxes, Earth itself can cast a shadow over the observatory. For a short while, the Sun is hidden, and SDO passes through a man-made night in space, its stream of solar images briefly broken. More rarely, the Moon glides across the Sun from SDO's point of view, a dark, round shape biting into the bright disk. These lunar transits create stunning silhouettes, but also mean that, for a little while, the spacecraft cannot see the full face of the star it is meant to watch. In the year 2016, SDO faced a different kind of eclipse, not from shadows in space, but from a problem deep within one of its most important instruments. The atmospheric imaging assembly, that delicate, many-eyed camera system that has given us so many views of the solar atmosphere, experienced technical difficulties. For a mission built around continuous, high-resolution imaging, any threat to AIA is serious. Losing or degrading that stream of data would have meant giving up some of our clearest insight into the Sun's dynamic behavior. The challenge was subtle. Scientists were trying to detect a particular kind of event, faint, elusive coronal mass ejections high in the corona, in regions where magnetic fields are weaker and the signals are much harder to see. Unlike the more obvious eruptions, which carve out visible dimmings in the corona and leave bold signatures in traditional images, these gentler events can pass almost unnoticed, hidden in slow, quiet changes. Rather than giving up, the team turned to new ways of looking at the same data. They began to compare each fresh image of the Sun with one taken many hours before, say, 12 hours earlier, searching for slow, creeping differences in the lower corona. This time-lapse way of seeing allowed subtle changes to emerge, slight shifts in brightness, gentle rearrangements of magnetic loops, faint dimmings that would have been easy to overlook in single snapshots. To enhance these whispers in the data, they applied advanced image processing techniques, with names as intricate as the patterns they revealed. Methods like wavelet packet equalization and multi-scale Gaussian normalization. In simpler terms, these approaches stretch and adjust the contrast of the images on many different scales at once, making faint structures stand out without drowning them in noise. With these tools, previously hidden dimmings and delicate motions came into view. What began as a technical difficulty became an opportunity. The refinements born from that challenge made SDO even better at catching the sun's quieter moods, not just its loudest flares. It is a small example of how, in space science, problems often turn into pathways to deeper understanding. As we follow these threads outward, we begin to see that the sun is not only an object of curiosity, it is an active presence shaping the space around it. The term space weather might sound poetic, but it has a very real meaning. It refers to the storms and winds of the sun, solar flares, coronal mass ejections, and streams of energetic particles that sweep through the solar system. When these outbursts travel outward, they carry energy and magnetic fields with them. If a coronal mass ejection is aimed toward Earth, its charged particles and embedded magnetic field can collide with our planet's own magnetic bubble, the magnetosphere. Sometimes the result is breathtaking, curtains of aurora shimmering near the poles, the northern and southern lights painting the sky with green and violet. Other times, the consequences are more troubling. Strong disturbances can disrupt satellites, interfere with radio communications, and in extreme cases, induce currents in power lines that strain electrical grids. Thanks in part to SDO's decade of watchfulness, scientists now have a much better understanding of the solar mechanisms that give rise to these events. By studying how magnetic fields twist, store energy, and finally release it in flares or coronal mass ejections, researchers can build models that predict when the sun is more likely to erupt and how those eruptions might unfold. Being able to forecast space weather, even with limited precision, buys us crucial time to protect satellites, adjust spacecraft operations, and safeguard power systems on Earth. The importance of this knowledge reaches beyond our own planet. As we send astronauts into space, whether in orbit near Earth, on journeys toward the Moon, or eventually onward to Mars and beyond, they will travel through regions where solar storms can pose serious risks. High-energy particles from the sun can damage electronics and increase radiation exposure. Understanding the rhythms and tempers of our star becomes a form of quiet protection for those who leave the safety of our atmosphere. In this way, the insights from SDO ripple outward. They help keep our technology safer, guide the planning of interplanetary missions, and deepen our sense of how intimately we are connected to the star that anchors our sky. And SDO is not alone. The present era of solar exploration is a kind of golden hour, rich with daring missions that complement one another. The Parker Solar Probe, launched in the year 2018, has been spiraling closer and closer to the sun with each orbit, dipping into the outer layers of the corona itself. It is the first spacecraft to truly fly within this mysterious region, tasting the solar wind where it is born and feeling the heat and magnetic turbulence up close. Meanwhile, the Solar Orbiter, a joint mission between the European Space Agency and NASA, launched around the year 2020, follows a carefully chosen path that will eventually tilt its orbit to peer over the sun's poles. Those polar regions have been historically hard to see, but are crucial for understanding how the solar magnetic field is organized on the largest scales. Solar Orbiter carries a rich suite of instruments to photograph the surface, measure the solar wind, and trace the structure of the magnetic field out into space. Together with SDO's steady gaze from geosynchronous orbit, these missions form a kind of distributed observatory. Parker's solar probe brings in situ measurements from deep within the corona. Solar Orbiter offers far-reaching perspectives, including views of the high latitudes. SDO provides continuous, high-resolution imaging of the full disk as seen from Earth. Each mission answers some questions and raises others, and all of them rely on each other's findings. As we look ahead, it feels as though we are standing at the threshold of a new kind of understanding. By teasing apart the threads of the sun's magnetic field, we come closer to explaining why some flares are gentle and others are explosive, why some coronal mass ejections are slow and harmless while others are fast and dangerous. By listening to the pulse of the 11-year solar cycle at many wavelengths and many vantage points, we begin to see patterns that were invisible before. And yet, even as we focus intensely on our own star, another thought quietly rises. The sun is one star among countless others. If we can learn so much from a decade of watching this one, what might we discover when we turn similar attention to stars scattered across the galaxy and to the planets that circle them? Imagine, for a moment, a universe filled not just with stars, but with small worlds carrying the raw materials for life, hidden in the dark around faint, ember-like suns. Some of the most promising places to look for alien life may not be the bright, sun-like stars we first imagined, but the smallest and dimmest ones, cool stars that burn slowly and live for trillions of years. Around these tiny stars, the James Webb Space Telescope has begun to find something remarkable. Rocky exoplanets, rich in carbon. With its exquisite sensitivity and powerful infrared eyes, the James Webb Space Telescope can peer back towards some of the earliest generations of stars, detecting delicate traces of carbon dust that formed as those first stars lived and died. That dust drifts through space, mixing with gas and seeding future generations of stars and planets. It is the quiet ash from which new worlds are built. Carbon is at the heart of organic chemistry, the backbone of DNA, proteins, and the countless molecules that make living cells possible. When we see signs of carbon-rich environments around small stars, it is hard not to wonder whether we are looking at laboratories where chemistry has been given enough time and stability to become something more, perhaps the long, slow experiments that one day produce life. These rocky planets, orbiting close to their dim suns, may enjoy relatively stable conditions for unfathomable spans of time. Their stars burn gently, not in a brief blaze like massive stars that die young, but in long, steady glows. If their surfaces are rich in carbon-bearing materials, bathed in modest warmth, and shielded by atmospheres of the right thickness, they could become places where complex organic compounds assemble, break, and reassemble again. All of this, though, rests on an even more basic structure. Before you can have life on a planet, you must have the planet itself. Before you can have a planet, you must have the swirling cradle where it forms. These nurseries are called protoplanetary disks, vast, rotating sheets and rings of gas and dust surrounding young stars. They are thin compared to their width, like cosmic records spinning slowly in the dark, full of tiny grains and icy specks waiting to grow. Within these disks, countless collisions take place. Dust grains stick together, forming pebbles, then boulders, then embryonic planetesimals. At the same time, chemistry blooms. Simple molecules meet and combine on the surfaces of grains and within icy mantles. Under the influence of radiation, heat, and time, they can grow more complicated, step by careful step. Protoplanetary disks are not just construction sites for planets. They are also the first kitchens where the essential ingredients for life are mixed together. Inside those thin, spinning cradles of gas and dust, the chemistry is anything but simple. With more sensitive instruments, we are starting to see just how rich and busy these places really are. Powerful observatories, such as the Atacama Large Millimeter Array in the high deserts of Chile, have turned their attention to protoplanetary disks and found a surprising variety of organic molecules hiding there. In the cold, dense regions of these disks, where sunlight is faint and temperatures are low, simple gases can begin to change. Molecules such as methane, formaldehyde, and acetylene appear in the spectra, each one a quiet signature written in the light. They form through intricate chains of reactions triggered by collisions between gas and dust, stirred by turbulence and gravity. Ultraviolet radiation from the young central star and the constant drizzle of cosmic rays provide just enough energy to rearrange atoms, nudging them into new shapes and bonds. Out of this gentle chaos, the first links in the long chain toward life are forged. Organic molecules are important because they represent the earliest steps on a path that, at least once in the universe, led to living cells. Simple compounds can serve as precursors to more complex structures, such as amino acids and nucleotides, the building blocks of proteins and DNA. When we detect these molecules in protoplanetary disks, we are not yet seeing life, but we are seeing the kinds of ingredients that life on Earth once used. Their presence suggests that the basic building blocks of biology may be forming naturally wherever planets are being born, not as rare oddities, but as a common outcome of disk chemistry. To probe these processes more deeply, scientists combine observations with laboratory experiments and detailed models. The James Webb Space Telescope, with its high-resolution infrared instruments, has greatly expanded our view. Infrared light is particularly good at revealing the vibrational fingerprints of molecules, allowing astronomers to identify specific species even when they are mixed together in distant clouds and disks. With Webb's help, researchers have detected a range of key molecules in planet-forming regions: water, CO2, and a variety of more complex organics. These detections show that the chemical environment of a disk is not uniform. Instead, it is a patchwork of different zones, each with its own temperature, density, and mixture of ices and gases. One especially important result from Webb's observations is the ability to map how different molecules are distributed with distance from the central star. In some regions, farther from the heat, ices accumulate on dust grains, forming mantles rich in water and organics. Closer in, where temperatures rise, some of those ices evaporate back into gas, changing the chemistry yet again. These maps reveal rings and layers where particular compounds are abundant, hinting at where future planets might gather certain ingredients. The picture that emerges is that young planets do not start as blank, sterile stones. As they grow within the disk, they sweep up dust and ice loaded with organic molecules. Some of these materials are preserved in comets and asteroids, frozen time capsules that can later fall inward and deliver their cargo to planetary surfaces. On a young world with oceans or a thick atmosphere, these deliveries can seed the surface with the raw material for further chemistry, nudging that world a little closer to habitability. Understanding the chemical structure of protoplanetary disks deepens our sense of how planets form and evolve. The presence of organics and other complex compounds tells us that, almost from the beginning, planetary building blocks are flavored in many different ways. The movement and mixing of material within the disk, dust drifting inward, gases flowing outward, pockets of turbulence stirring things up, can lead to planets with very different compositions and atmospheres, even within the same system. That diversity is not just a curiosity. It is crucial for creating a range of planetary environments, some harsh, some gentle, and a few perhaps welcoming to life. Among Webb's many discoveries, one has a particular shimmer to it: the detection of dust made of diamond-like carbon from some of the universe's earliest stars. Using its sensitive infrared eyes, the telescope can pick out the faintest traces of light from ancient galaxies. In those spectra, scientists have found features best explained by tiny grains of carbon arranged in crystalline structures, reminiscent of diamonds here on Earth. Carbon dust plays a critical role in the early cosmos. In the cold interiors of giant molecular clouds, the birthplaces of stars, it helps gas cool down. By radiating away heat, the dust allows the clouds to collapse under gravity, fragmenting into dense clumps that can ignite as new stars. Without this cooling, star formation would be much harder, and the universe would look very different. As stars live and die, particularly the massive ones, they create heavy elements such as carbon in their cores. When these stars explode or shed their outer layers, they spit that carbon back into space in dust and gas, enriching the interstellar medium. Over time, this recycled material becomes part of new clouds, new disks, and new generations of stars and planets. In protoplanetary disks, carbon dust contributes to the solid component. Grains can stick together, forming pebbles and larger aggregates that eventually become the rocky cores of planets. The presence of diamond-like carbon dust so early in cosmic history tells us that carbon became abundant surprisingly quickly after the Big Bang. It hints that the conditions for forming carbon-based molecules, and therefore at least one of the key ingredients for life, may have existed far earlier than once assumed. This fits with theories about the first stars, often called population 3 stars, which formed from pristine hydrogen and helium not long after the universe began. As those massive stars burned and died, they seeded space with newly forged carbon and other heavy elements, setting the stage for more chemically complex eras to come. In a very real sense, a carbon-rich universe is a universe with greater potential for life as we know it. Carbon is uniquely versatile. Each carbon atom can form stable bonds with 4 other atoms at once, allowing it to build long chains, branching structures, and intricate rings. These flexible frameworks become the backbone for an enormous variety of organic molecules, from simple gases to the sprawling, folded structures of proteins. Without this ability to form complex, stable, yet adaptable molecules, the chemistry of life would struggle to get off the ground. Even more intriguing are Webb's glimpses into specific planet-forming disks around small, dim stars in our own galaxy. In one study released in June of a recent year, a team of more than 40 scientists combined their efforts to peer into the disk surrounding a young star called ISO Cha I-147 in the Chameleon, one star-forming region. What they found there was described as the richest menu of hydrocarbons ever observed in a planet-forming disk. Within that disk, Webb's instruments detected a whole family of carbon-bearing molecules. Among them was something never before clearly seen outside our own solar system: ethane. Ethane is a simple hydrocarbon, 2 carbon atoms and 6 hydrogen atoms, but its presence is important. It can act as a stepping stone in chemical pathways that lead to more complex organics. Finding ethane in a young disk suggests that the chemistry there is already busily exploring routes toward greater molecular complexity. The observations of ISO CHA I-147 hint at something else as well. The disk around this small star appears to be particularly efficient at building the kind of solids that could grow into Earth-like planets rather than the enormous gas giants we see farther out in some systems. That matters because low-mass stars, smaller and cooler than the Sun, are by far the most common type of star in the Milky Way. If their disks are especially good at assembling small, rocky worlds, then our galaxy might hold far more terrestrial planets than we once imagined. Chemically, the disk is striking. Astronomers counted at least 13 different carbon-containing molecules, including ethane and benzene, present in significant amounts. At the same time, they found relatively low abundances of oxygen-bearing molecules, such as water and CO2. This is quite different from many disks around stars, more like the Sun, where oxygen-rich compounds often dominate the inventory. Such a carbon-heavy, oxygen-light mixture suggests that the basic ingredients available to build planets there are shifted in favor of certain types of chemistry. If a planet forms in a region where hydrocarbons are plentiful and water and CO2 are comparatively scarce, its atmosphere and surface may end up very different from those of Earth. It might have more carbon-rich rocks and gases, and less of the familiar combination of water vapor and CO2 that shapes climates on worlds like ours. The presence of so many hydrocarbons in this disk also hints that material is moving around in subtle ways. To gather that variety and abundance in certain locations, dust and gas likely have to drift inward and outward, carrying ices and organics from the colder outer zones toward warmer inner regions and back again. This radial transport, the slow reshuffling of matter along the disk, gently alters the blend of elements and molecules that fall together to make each planet. In other words, the chemistry we see in ISO CHA I-147's disk is not just a static snapshot. It is a sign that the disk is actively rearranging its ingredients and that this movement is quietly shaping the fundamental composition of the planets that are beginning to form within it. The shifting chemistry in that small star's disk hints at more than just pretty spectra. It suggests that, as rocky worlds slowly gather from dust and ice, they may inherit very different starting recipes from the one Earth received. If the ingredients are different, the air those planets eventually breathe could be different too. Around tiny, cool stars, some rocky planets may grow in regions where hydrocarbons are abundant, but oxygen-bearing molecules are relatively scarce. In such places, the first atmospheres that wrap around young worlds might be dominated by carbon-rich gases instead of oxygen-rich mixtures like the one we know. Imagine planets where hazy skies of methane and other hydrocarbons are the norm, and where the air glows in unfamiliar colors when starlight filters through. These would be carbon-rich worlds with atmospheres that do not closely resemble our own. Finding environments like this matters deeply for any quiet search for life. Carbon is the backbone of organic chemistry, supporting DNA, proteins, and countless other molecules that keep Earth's cells alive and active. When we see similar carbon-bearing compounds in planet-forming disks, it tells us that the earliest steps toward complex chemistry might be common, arising naturally as planets take shape. Life as we know it is not guaranteed in such places, but the raw materials are there. The imbalance between carbon and oxygen seen in some disks is also a clue to the restless nature of these systems. One possible picture is that solid grains, dust, and pebbles lose part of their carbon as they migrate, releasing it into the gas. The solids that eventually merge into planetary cores become relatively poor in carbon, forming rocky bodies with compositions more like silicate and metal. Meanwhile, the gas they leave behind becomes relatively rich in carbon-containing molecules. When that gas is later gathered into an atmosphere, the resulting world can end up with a rocky, carbon-poor interior wrapped in a carbon-dominated sky. Distinguishing between carbon-rich and oxygen-rich disks helps us imagine the kinds of planets that might emerge. In disks where hydrocarbons such as ethane are abundant, you might expect atmospheres that favor very different biochemical pathways from the ones Earth's life uses. In oxygen-rich disks, where water and carbon dioxide are plentiful, the conditions may echo the early Earth more closely, a world with liquid water and a mix of gases that can support the familiar sorts of carbon-based chemistry. This chemical diversity means that the planets forming in these different environments could have wildly different atmospheres and surface conditions. Some might be hot, hazy, and shrouded in organic smog, others cold and icy, others temperate and wet. In some of them, strange prebiotic chemistries could unfold that we can barely guess at now. It is a reminder that life, if it appears elsewhere, may look and behave in ways that stretch our imagination. The discovery of rocky, carbon-rich exoplanets around small stars does more than add a few exotic entries to a catalog. It broadens our understanding of what planetary systems can be, and quietly strengthens the hope that life might not be unique to Earth. Small stars, those cool, dim embers that astronomers call red dwarfs, are extremely common in the Milky Way. They live for unimaginably long times, often far longer than stars like our Sun, burning their fuel slowly and steadily. That stability offers a long window for any emerging life to develop and evolve. But carbon alone is not enough. When we look for places where life might arise, we also pay close attention to something both simple and profound: liquid water. This is where the idea of the habitable zone comes in, sometimes called the Goldilocks zone. The region around a star where temperatures could allow liquid water to exist on a planet's surface, not entirely frozen and not entirely boiled away. Habitable zones shift depending on the type of star. Around small, cool stars, the zone of just right temperatures lies close in, where planets must huddle tight to stay warm. Around larger, hotter stars, that comfortable band lies farther out. Identifying planets in these Goldilocks zones is a central goal in the search for potentially habitable worlds, because water as a liquid is such a powerful solvent, able to host the complex chemistry needed for biology. To find such planets, astronomers use delicate instruments that can sense tiny tugs and flickers in starlight. One of these tools is the Habitable Zone Planet Finder, often abbreviated as HPF. Mounted on the Hobby Eberly telescope in Texas, HPF is designed to look at low-mass stars and measure minute changes in their light caused by the gravitational pull of orbiting planets. As a planet circles a star, it makes the star wobble slightly. That wobble shows up as a tiny shift in the star's spectrum. HPF is especially well suited to hunting planets in the habitable zones of these cool, dim stars. By focusing on the stars that are most common in the galaxy, it gives us a much better chance of finding Earth-sized planets at just the right distances. Its precision is high enough to detect small, rocky worlds that would be invisible to less sensitive instruments. Within this context of careful, patient searching, a particularly surprising discovery has emerged. A planet called LHS 3154b. This exoplanet orbits a relatively small star, yet it is unexpectedly massive for its host. Traditional models of planet formation, such as the core accretion scenario and disk instability models, generally suggest that the mass of a star places limits on how large its planets can grow. A small star usually has less material in its disk, making it harder to form very massive planets. LHS 3154b does not seem to follow that rule. Its existence hints that there are mechanisms at work in planet formation that we still do not fully understand. Perhaps this planet formed farther out in the disk, in a region richer in solids, and then migrated inward over time. Perhaps it was once part of another system and was captured. Each possibility invites new questions about how planetary systems grow and change. What makes this discovery even more intriguing is that LHS 3154b appears to reside in a region where liquid water could, in principle, exist on a planetary surface if other conditions were right. Its presence suggests that habitable zones may exist in a broader range of stellar environments than we once thought. At the same time, such a massive planet residing in or near the habitable zone of a small star could strongly influence the orbits and climates of any smaller neighbors. Its gravity might shepherd smaller, potentially habitable planets into stable, gentle paths, or it might disturb them, making their climates erratic and challenging for life. The unusual size and orbit of such a planet also make astronomers think about the long-term evolution of worlds. Some gas giants may lose significant parts of their atmospheres over time, stripped away by intense radiation from their stars or by gravitational tides during close encounters. This process, sometimes called planetary evaporation or atmospheric escape, can reshape a planet's mass and size. In the case of LHS 3154b, its large mass and strange orbit could be the outcome of such processes, or the starting point of them. It may have begun as an even larger gas giant, or formed in a different part of its stellar system before migrating inward under the complex gravitational influences of the disk and the star. Discoveries like this gently undermine the old idea that only Earth-like planets around Sun-like stars are worth considering when we talk about habitability. They suggest a universe where life could, in principle, arise in many different settings, around small stars, in systems with massive neighbors. Under skies lit by red suns, our catalog of known worlds is pushing us to widen our imagination. As we keep scanning the sky, the study of exoplanets has become one of the brightest threads in modern astronomy. Current and planned space missions promise to transform our understanding of these distant worlds, especially those in habitable zones. One key mission already in operation is the Transiting Exoplanet Survey Satellite, usually called TESS, launched in the year 2018. TESS watches large swaths of the sky, looking for tiny, regular dips in starlight that occur when a planet passes in front of its star, briefly dimming it. TESS focuses on relatively bright stars close to Earth, so that any planets it finds can be studied in more detail by other telescopes. It has already discovered many exoplanets, some of them in their stars' habitable zones, making them prime candidates for deeper investigation. Each of these planets becomes a potential story, a place where we might someday measure an atmosphere or search for hints of clouds, oceans, or other features. Looking ahead, the European Space Agency is preparing a mission known as ARIEL, short for Atmospheric Remote Sensing Infrared Exoplanet Large Survey. Scheduled for launch in the late 2020s, ARIEL is designed to study the atmospheres of about 1,000 exoplanets. By analyzing the infrared light that filters through or reflects from those atmospheres, it will reveal their chemical compositions and temperature structures. That, in turn, will help scientists piece together how different planetary systems form and change, and which conditions might be more favorable for life. Farther on the horizon, proposed missions with names like LUVOIR and HABEX imagine even more ambitious steps. Their goal would be to directly image Earth-like planets around nearby stars, separating the faint glow of a planet from the overwhelming glare of its star. By spreading that light into a spectrum, astronomers could look for signs of gases like oxygen and methane coexisting in ways that might hint at biological activity, so-called biosignatures. These future observatories would not just detect planets, they would begin to characterize them as places with skies, climates, and possibly, in some rare cases, hints of something living. They are still ideas, plans, and designs on paper, but they point toward a time when we may look at a pale dot of light and know not just that it exists, but that its air holds the fingerprints of chemistry we cannot easily explain without life. All of these efforts, watching disks and dust, mapping hydrocarbons, tracking tiny dips in starlight, sifting spectra for faint fingerprints, add up to a slow, patient exploration of the question that lingers behind so much of our curiosity. As we learn more about these distant worlds, their exotic chemistries, and their varied suns, the question grows softer and more insistent, like a whisper at the edge of sleep. Are we alone in this vast universe? Or is life quietly waiting to be discovered on worlds we have only just begun to see? When we wonder whether life might be waiting on distant worlds, it is almost impossible not to glance back, just for a moment, at our own beginnings. Before we can guess what may be possible out there, we need to remember what happened here, how a lifeless planet became a place of oceans, forests, and eventually, quiet human questions whispered into the night. Most of us are used to the idea that life on Earth began in the sea. It feels natural. The oceans cover more than 70% of our planet's surface, and even today, they are crowded with creatures, many of them still only dimly known. New species are discovered in the depths every year, hiding in darkness and pressure our bodies could never survive. From that watery cradle, life slowly, patiently made its way onto land, adapting step by step until, far down the line, one branch of that immense family tree gave rise to us. We often picture this as a slightly comical scene from a school book. Some ancient fish one day decides to haul itself up onto a beach for a walk. Darwin's own sketches and the many retellings of his ideas have shaped that image. Modern science paints a gentler, slower story of fins turning into sturdier limbs over countless generations, of lungs evolving alongside gills, of shallow lagoons and muddy shores where it was useful, not whimsical, to push a little farther out of the water. But even with all these details, big questions remain. How exactly did life manage that difficult transition from buoyant water to harsh, dry land? Why would a violent meteorite strike ever help, rather than simply destroy? Could a collision with another planet actually be important for making a world more suitable for life? What did Earth look like in its first few million years? And what obstacles did it have to survive before even a single cell could appear? Some of these questions now have partial answers, stitched together from rocks, models, and starlight. To follow them, we have to travel far back in time, not just to the early Earth, but to the early universe itself. In the beginning, long before there were stars, there were no planets at all. Astronomers think that our universe burst into being in a single, hot, dense event, often called the Big Bang, roughly between 13 and 14 billion years ago. In those first moments, space expanded, and the simplest elements appeared. Hydrogen, the lightest of them all, filled young space like a thin fog. Under gravity, clumps of it gathered, grew denser, and heated until deep inside, hydrogen atoms began to fuse into helium. When that happened, a new kind of object was born, a protostar, the seed of a future star. These early stars were more than just bright points. Inside them, nuclear reactions forged heavier elements: carbon, oxygen, silicon, iron. When massive stars reached the ends of their lives, some exploded as supernovae, flinging those newly made elements out into space. In this way, stars acted like enormous cosmic factories, turning simple ingredients into the complex periodic table we now know, and seeding the universe with the raw materials that would one day make planets, oceans, and living cells. Our own sun is one such factory, still steadily burning hydrogen into helium in its core. Like all stars, it follows a life cycle. It is born from a collapsing cloud, shines for billions of years, and eventually changes into a new form. For the sun, the most likely path is to swell into a red giant in the far future, expanding so much that it will engulf or scorch the inner planets, including Earth, before shrinking into a dim white dwarf. That fate lies roughly 5.5 billion years ahead, far enough that every story we tell now will have long finished by then. What makes our solar system special is the particular way its story seems to have begun. Many scientists think that, near the region where our system was forming, a nearby massive star reached the end of its life and exploded. The shockwave from that supernova may have helped compress a cloud of gas and dust, nudging it into collapse. Under the pull of gravity, the cloud flattened into a spinning disk. At the center, material piled up so densely that the sun ignited. Around it, leftovers from that collapse continued to swirl, forming a broad disk of gas, ice, and dust. Not everything was swept into the newborn star. In the disk, countless small clumps collided and stuck together, growing into larger and larger bodies. Some became the planets. Others remained as asteroids, comets, and dwarf planets, straggling stones and icy fragments circling in wider orbits. Somewhere in that busy disk, at just the right distance from the young sun, the early Earth took shape. In its youth, our planet would have been unrecognizable to us. Imagine a world without blue oceans or green continents, just a churning surface of molten rock, a global ocean of lava. Above it, the air was not breathable but harsh, a mixture of carbon dioxide, nitrogen, and steam. The gases released as the crust melted and boiled. Near the surface, temperatures may have climbed to something like 1,200 degrees, hot enough to keep most rocks soft and glowing. At the same time, the infant solar system was a rough playground. Leftover comets and meteorites still swarmed in great numbers, many of them drawn toward Earth and the Sun by gravity. These bodies crashed into the young planet again and again, punching craters into the still-forming crust, adding their own minerals and ices to the mix. The seeds of our water may have been tucked inside some of these icy visitors, but for a while, there was no stable ocean, no gentle rain, only steam and fire. Then came a single collision that changed everything. A wandering planet, roughly the size of Mars, which scientists later named Theia, is thought to have struck the early Earth in a glancing, catastrophic blow. The impact partially melted both bodies, flinging huge amounts of material into space. The Earth's shape and size were altered, and over time, the debris coalesced into a companion, our moon. In those early days, the moon did not hang as far away as it does now. It may have orbited much closer, at a distance of only about 13,600 miles. Its gravity would have raised enormous tides on the young Earth, stirring the oceans once they formed and perhaps playing a role in the mixing of chemicals along early shorelines. Over billions of years, the moon has slowly drifted outward, but its influence on tides, on the stability of Earth's tilt, and therefore on our seasons, remains quietly profound. As time passed, the planet began to cool. A solid crust formed over the once molten surface, cracking into plates that would later drift and collide in slow plate tectonics. Gases accumulated into a thicker atmosphere, held in place by Earth's gravity. Deep inside, the core of the planet remained molten iron, swirling and churning. That moving metal acts like a dynamo, generating a magnetic field that wraps around the Earth and helps shield it from charged particles streaming out from the sunday. The magnetic field also plays a role in the way our planet spins, contributing to the long-term stability of its rotation. Eventually, as temperatures dropped, something new began to happen. Water vapor in the atmosphere could condense. Around 3.8 billion years ago, the young Earth was struck by a prolonged meteor shower, a heavy late bombardment of leftover debris from the solar system's formation. Many of these impacting bodies carried small amounts of water locked up in minerals or frozen in ice. Each meteorite delivered only a tiny contribution, but the bombardment continued for millions of years. At that time, Earth was spinning much faster than it does today. A full rotation may have taken only around 6 hours, making days short and nights brief. Under such conditions, rainstorms would have come and gone under a rapidly turning sky. These were not gentle showers as we know them, but torrents falling on hot rock, hissing into steam, then condensing again. Over roughly 20 million years of bombardment and cooling, water began to accumulate in low places, filling basins, turning them into the planet's first oceans. This raised a natural question that has bothered scientists for decades. Where, exactly, did all of Earth's water come from? One school of thought suggested that nearly all of it was delivered from space by comets and meteorites, like a long, slow delivery service from the outer solar system. Another idea held that much of the water was already here, trapped in minerals in Earth's interior, and gradually released through volcanic activity as the planet cooled. The answer, it seems, is not simple. Samples brought back from the moon, combined with careful study of lunar soil, have shown that the young sun was far more active than it is today. Its radiation was intense enough to strip away light gases and anything that could easily evaporate, including water, from the surfaces of the inner planets. That means some early stores of water may have been lost and later replaced, while other portions remained locked away deeper inside. When scientists compare the chemical fingerprints of water in meteorites, in Earth's oceans, and in volcanic rocks, they find a mixture of clues that point in both directions. Some isotopic signatures suggest an extraterrestrial contribution. Others hint at a native, deep Earth source. As new data arrives, models are refined, but no single story has won the day. And so, even after all our progress, one of the simplest questions, where did our water truly come from, remains partly unanswered. Scientists still cannot definitively say whether there is more water of meteoric or terrestrial origin present on Earth, and most likely, they will never be able to answer that question. When we wonder whether life might be waiting on distant worlds, it is almost impossible not to glance back just for a moment, at our own beginnings. Before we can guess what may be possible out there, we need to remember what happened here, how a lifeless planet became a place of oceans, forests, and eventually, quiet human questions whispered into the night. Most of us are used to the idea that life on Earth began in the sea. It feels natural. The oceans cover more than 70% of our planet's surface, and even today, they are crowded with creatures, many of them still only dimly known. New species are discovered in the depths every year, hiding in darkness and pressure our bodies could never survive. From that watery cradle, life slowly, patiently made its way onto land, adapting step by step until, far down the line, one branch of that immense family tree gave rise to us. We often picture this as a slightly comical scene from a school book. Some ancient fish one day decides to haul itself up onto a beach for a walk. Darwin's own sketches and the many retellings of his ideas have shaped that image. Modern science paints a gentler, slower story of fins turning into sturdier limbs over countless generations, of lungs evolving alongside gills, of shallow lagoons and muddy shores where it was useful, not whimsical, to push a little farther out of the water. But even with all these details, big questions remain. How exactly did life manage that difficult transition from buoyant water to harsh, dry land? Why would a violent meteorite strike ever help rather than simply destroy? Could a collision with another planet actually be important for making a world more suitable for life? What did Earth look like in its first few million years? And what obstacles did it have to survive before even a single cell could appear? Some of these questions now have partial answers, stitched together from rocks, models, and starlight. To follow them, we have to travel far back in time, not just to the early Earth, but to the early universe itself. In the beginning, long before there were stars, there were no planets at all. Astronomers think that our universe burst into being in a single, hot, dense event, often called the Big Bang, roughly between 13 and 14 billion years ago. In those first moments, space expanded, and the simplest elements appeared. Hydrogen, the lightest of them all, filled young space like a thin fog. Under gravity, clumps of it gathered, grew denser, and heated until, deep inside, hydrogen atoms began to fuse into helium. When that happened, a new kind of object was born, a protostar, the seed of a future star. These early stars were more than just bright points. Inside them, nuclear reactions forged heavier elements: carbon, oxygen, silicon, iron. When massive stars reached the ends of their lives, some exploded as supernovae, flinging those newly made elements out into space. In this way, stars acted like enormous cosmic factories, turning simple ingredients into the complex periodic table we now know, and seeding the universe with the raw materials that would one day make planets, oceans, and living cells. Our own sun is one such factory, still steadily burning hydrogen into helium in its core. Like all stars, it follows a life cycle. It is born from a collapsing cloud, shines for billions of years, and eventually changes into a new form. For the sun, the most likely path is to swell into a red giant in the far future, expanding so much that it will engulf or scorch the inner planets, including Earth, before shrinking into a dim white dwarf. That fate lies roughly 5.5 billion years ahead, far enough that every story we tell now will have long finished by then. What makes our solar system special is the particular way its story seems to have begun. Many scientists think that, Near the region where our system was forming, a nearby massive star reached the end of its life and exploded. The shock wave from that supernova may have helped compress a cloud of gas and dust, nudging it into collapse. Under the pull of gravity, the cloud flattened into a spinning disk. At the center, material piled up so densely that the sun ignited. Around it, leftovers from that collapse continued to swirl, forming a broad disk of gas, ice, and dust. Not everything was swept into the newborn star. In the disk, countless small clumps collided and stuck together, growing into larger and larger bodies. Some became the planets. Others remained as asteroids, comets, and dwarf planets, straggling stones and icy fragments circling in wider orbits. Somewhere in that busy disk, at just the right distance from the young sun, the early Earth took shape. In its youth, our planet would have been unrecognizable to us. Imagine a world without blue oceans or green continents, just a churning surface of molten rock, a global ocean of lava. Above it, the air was not breathable but harsh, a mixture of carbon dioxide, nitrogen, and steam. The gases released as the crust melted and boiled. Near the surface, temperatures may have climbed to something like 1200 degrees, hot enough to keep most rocks soft and glowing. At the same time, the infant solar system was a rough playground. Leftover comets and meteorites still swarmed in great numbers, many of them drawn toward Earth and the sun by gravity. These bodies crashed into the young planet again and again, punching craters into the still-forming crust, adding their own minerals and ices to the mix. The seeds of our water may have been tucked inside some of these icy visitors, but for a while, there was no stable ocean, no gentle rain, only steam and fire. Then came a single collision that changed everything. A wandering planet roughly the size of Mars, which scientists later named Theia, is thought to have struck the early Earth in a glancing, catastrophic blow. The impact partially melted both bodies, flinging huge amounts of material into space. The Earth's shape and size were altered, and over time, the debris coalesced into a companion, our moon. In those early days, the moon did not hang as far away as it does now. It may have orbited much closer, at a distance of only about 13,600 miles. Its gravity would have raised enormous tides on the young Earth, stirring the oceans once they formed, and perhaps playing a role in the mixing of chemicals along early shorelines. Over billions of years, the moon has slowly drifted outward, but its influence on tides, on the stability of Earth's tilt, and therefore on our seasons, remains quietly profound. As time passed, the planet began to cool. A solid crust formed over the once molten surface, cracking into plates that would later drift and collide in slow plate tectonics. Gases accumulated into a thicker atmosphere, held in place by Earth's gravity. Deep inside, the core of the planet remained molten iron, swirling and churning. That moving metal acts like a dynamo, generating a magnetic field that wraps around the Earth and helps shield it from charged particles streaming out from the sunday. The magnetic field also plays a role in the way our planet spins, contributing to the long-term stability of its rotation. Eventually, as temperatures dropped, something new began to happen. Water vapor in the atmosphere could condense. Around 3.8 billion years ago, the young Earth was struck by a prolonged meteor shower, a heavy late bombardment of leftover debris from the solar system's formation. Many of these impacting bodies carried small amounts of water locked up in minerals or frozen in ice. Each meteorite delivered only a tiny contribution, but the bombardment continued for millions of years. At that time, Earth was spinning much faster than it does today. A full rotation may have taken only around 6 hours, making days short and nights brief. Under such conditions, rainstorms would have come and gone under a rapidly turning sky. These were not gentle showers as we know them, but torrents falling on hot rock, hissing into steam, then condensing again. Over roughly 20 million years of bombardment and cooling, water began to accumulate in low places, filling basins, turning them into the planet's first oceans. This raised a natural question that has bothered scientists for decades. Where, exactly, did all of Earth's water come from? One school of thought suggested that nearly all of it was delivered from space by comets and meteorites, like a long, slow delivery service from the outer solar system. Another idea held that much of the water was already here, trapped in minerals in Earth's interior and gradually released through volcanic activity as the planet cooled. The answer, it seems, is not simple. Samples brought back from the moon, combined with careful study of lunar soil, have shown that the young sun was far more active than it is today. Its radiation was intense enough to strip away light gases and anything that could easily evaporate, including water, from the surfaces of the inner planets. That means some early stores of water may have been lost and later replaced, while other portions remained locked away deeper inside. When scientists compare the chemical fingerprints of water in meteorites, in Earth's oceans, and in volcanic rocks, they find a mixture of clues that point in both directions. Some isotopic signatures suggest an extraterrestrial contribution. Others hint at a native, deep Earth source. As new data arrives, models are refined, but no single story has won the day. And so, even after all our progress, one of the simplest questions, where did our water truly come from, remains partly unanswered. Scientists still cannot definitively say whether there is more water of meteoric or terrestrial origin present on Earth, and most likely, they will never be able to answer that question.